Okay, I think that's a good point to start. Thank you for being with us at 3 in the afternoon. We've still got a good sized crowd. So my name is Professor Rosalind Archer. I'm the head of the Department of Engineering Science, and it's really a privilege to have that role. It's a really, really exciting place. So I've done 2 lectures so far today talking about engineering science as both the home of an engineering science degree and a biomedical degree. So those lectures kind of merged both. This lecture is a little different. It focuses on some of the work we do specifically in engineering science on energy. So engineering science is a degree that is ultimately all about mathematically based problem solving. And we're a bunch of problem solvers that like to do things that kind of have impact in the world. And energy is a very natural area where we can have impact. It's something that sort of touches all of our lives, cuts across the research that many of us do. So this lecture just looks at some of the kind of industries that we touch and engage with. So I'm going to kick off with just a little bit about my perspective, because when it comes to energy, it can be a bit of a contentious issue at times. So I'm an energy geek. I have 5 kilowatts of solar on my roof. I do now own a Tesla Powerwall battery. I live way, way out west where we tend to fall off the grid. I buy electricity that's carbon neutral, I drive an electric vehicle, I don't eat meat, and I do have an addiction to jet fuel, which kind of cancels out most of the above. But that just gives you a sense of kind of where I'm coming from, that I do sort of live this in my personal life as well as my professional life. In fact, in my personal life, I've made a commitment to go carbon neutral by buying carbon offsets at the end of the year. But again, my addiction to jet fuel, bit of a problem. A quick disclaimer, I do have connections to a range of other organisations, but everything I'm presenting is strictly my opinion and nobody else's. So, what do we do in engineering science in the energy sector? Part of what we do helps keep the lights on. So, behind the scenes in New Zealand, the power price, the electricity price, is changing every 30 minutes. And it's changing every 30 minutes because every 30 minutes there's a process where the electricity generators, so whether that's people sending water out through dams, people running wind farms, people burning gas and coal, every 30 minutes those companies make a call to say how much electricity they're prepared to generate in the next half hour and what price they're prepared to sell it at. And that creates a market, and that market settles in a way that has a price that bounces up and down like this. And the mathematics behind that pricing process is, at its core, an example of what's called operations research. So operations research is one of the styles of mathematics that we work on. So there's a really sophisticated bunch of equations that get solved, and those equations determine the price of the electricity and whose electricity gets fed into the mix. So this little graph here shows what type of electricity, whether it's generated from geothermal, hydro, gas, coal, etc. The fact that on the day I grabbed the shot, we were grabbing a bunch of electricity from the South Island, and the price was bouncing up and down. So this price behaviour can then feed into the behaviour of consumers, both retail and industrial. So I drive an electric car, so I put my car on a timer and I try and charge it here. Because electricity at 2 in the morning, traditionally really, really cheap. I don't do a lot of driving at 2 in the morning, I try and avoid it. So we have my car on to charge then. Solar panels, batteries, you can play games in terms of understanding when prices are high in terms of what you want to use. So that piece, that is driven by people who work with the skills that our degree builds, both working for the kind of government regulator, but also working for energy companies in terms of energy companies deciding how much electricity they're going to put into the market. The problem with that market is intermittency. So these are my solar panels, and this was a snapshot in time. Well, axis seems to have fallen off here, but this is 24 hours, well actually just the sunny part of the day, so less than 24 hours. But these increments show, I think they're probably little 10-minute bars, show the generation at my house. So clearly something happened here. Big cloud came over, cloud blows away, generation spikes up to pretty decent levels for summertime, but it's very, very spiky. So one of the things that anyone dealing with the market has to manage in terms of getting renewables in, wind and solar renewables, intermittent ones in, is how to deal with this in such a way that we do keep the lights on in the entire country. So dealing with that uncertainty is another aspect that the mathematics we do in the department helps the market manage. We have a range of other folks on campus who are interested in energy. So I do just want to acknowledge our campus energy manager, Russell Baillie. So he works for the university on managing our energy footprint. This is his house. It's in Mount Eden. It's a net zero home. So he actually produces more energy from that house than he uses through clever design, through solar panels, through storage and batteries, thermal mass in the concrete, all sorts of tricks. So he's a really interesting example of the kind of technologies that we think about. So we start to think about, what would cause disruption in an energy market. So one of the sort of disruptive technologies is solar. So we think about, here we've got the price of solar against time, predicted prices in either US dollars or British pounds, and that price is falling very steeply. So any other energy technology that's coming in has to essentially compete against falling solar prices. More of an issue in countries that have better solar resource than we do. New Zealand's not necessarily known for its sunshine. Parts of New Zealand are better than others. But at a global scale, solar is something that's very, very important. I work professionally on geothermal energy. So geothermal energy is the idea of getting hot water and steam up from under the ground. So in that area, we use another part of the maths we do in engineering science called continuum mechanics, where I'm interested in the equations that govern fluid flow, the equations that govern heat transfer, the equations that govern mechanical stresses and strains. So geothermal energy, we do a lot of prediction to say, what will the temperature be? What will be the flow rate at a well at a certain point? How long will that flow rate last? So if I drill a well and it dies in 2 years' time, and I've spent $10 million to drill it, is that a good idea? Probably not. But if that well lasts for 20 years, then it probably is a good idea. So we have been involved in this incredible growth in geothermal energy in this country. We have a very active partnership with the geothermal generation companies. We have a bunch of staff in the department who are very active in the consulting space, and that engages with our students, both our undergraduates and our postgraduates, in doing things that directly support growth of geothermal energy in the country. Is geothermal energy perfect? No. Okay, so geothermal energy does have some carbon emissions, so it does get into the media a little bit, but it has much, much lower emissions than fossil fuels. And the reason it has carbon emissions is because the fluids that come up from underground actually have some dissolved carbon dioxide in them, and some of that carbon dioxide does get released. But one of the things that I find really exciting about geothermal, and that I really love being part of the geothermal industry, is its impact on communities. So I find it exciting that geothermal is often a community-owned resource. So in New Zealand, our geothermal resource is typically owned by Maori communities through settlement processes in Northland at Ngāwhā, and most of the resource in the central North Island as well. So our geothermal companies are working either in partnership with Maori or are Maori owned themselves. And Maori owned enterprises have a very important view on sustainability. They want there to be geothermal energy for their great-great-grandchildren. They're not necessarily so concerned about sort of the short 10, 20-year timescales that other structures may worry about. And I love the fact that the work we do trying to predict the future behaviour of these geothermal systems supports their view on sustainability and supports generation of dividends that go through Maori trusts out to Maori communities. This shot here is a shot from Africa, from an exchange between Maori tribes from the Taupo region with the Maasai in Africa, looking at how geothermal development can be furthered in Africa and the Maori sharing their knowledge on the sort of success of the partnerships involved. The image below is in Iceland, where geothermal again is a really, really important part of their community. Because getting out and about in Iceland, you want to go somewhere warm. So some of the hot pools, you know, going to the local hot pool is the equivalent of going to the local pub or the local cafe. That's where you go to kind of hang out and meet people. Another energy form that we're interested in, more at the level of the entire faculty, is biofuel. So here's a picture, it's a little bit old, of Helen Clark at a Gull petrol station. They're introducing a biofuel blend that involves milk processing waste, but Gull has a range of biofuel options, including waste from meat processing. And some of that work was done by our sort of neighbours in chemical engineering in terms of pioneering the processes that make it possible. So we're quite interested in the whole sort of energy market in terms of understanding for any of those biofuel options, what kind of supply do you need to make the biofuel? Are you displacing something else in terms of use of land in other ways? What does that do to the price, etc.? So this biofuel currently is still more expensive than standard fossil fuel blends, but there are companies prepared to pay a premium for it. In the electric vehicle space, we're interested in electric vehicles. So this plot is number of electric vehicles in New Zealand against time, so fully electrics, not just the Prius silent colour hybrid, but these are full electrics, or plug-ins. So the growth in electrics is huge. I got mine somewhere in here, was about 1,200 on the road when I got mine. But electric vehicles are not without their challenges. I drive an entry-level vehicle, the first generation Nissan Leaf. Battery's getting a bit old, so I can only drive about 100 kilometres. Given that I live 35 kilometres from the office, that is a constraint. So we've had students get involved with trying to help adoption of electric vehicles by thinking about some of the mapping technologies. So if I'm making a map of where I want to drive, I'm not necessarily so concerned about distance. I'm concerned about things like hills, because I use a lot more energy to go uphill. I gain some energy coming back down, but not all of it. I'm concerned about things like road surfaces. So if I drive on a nice smooth road, I use a lot less energy than a really grungy country kind of a road where there's more friction in the tyres and I use my battery faster. So we've had a final year student work on basically coming up with a tweaked version of kind of a Google Map technology to say, okay, my battery's this big, how far can I drive? Where can I actually go, taking into account the topography, the hills, and the road surface? We've also got people in the operations research side of it who have an interest in government policy and who are quite interested in, for instance, the government's fee-bait situation where they're trying to encourage electric vehicle adoption, and they can make sort of models, I think, models of how people will behave and test out some things like that. As far as I know, they are supportive of the fee-bait proposal. We've had people in the department work on electric buses. So electric buses are coming into New Zealand, and they are quite a major disruptor in terms of energy. But again, the routes have to be planned, the charging options have to be planned so they can get back to their base, because you don't want to be on a bus home and you get 80% of the way there and then go, oh, my battery's flat, I'm stuck. It's a bit hard to bring out a petrol can. So this graph talks globally about the amount of fossil fuel that's been displaced by vehicles going electric, and the diesel conversion of diesel buses to electric is huge. So this is in thousands of barrels per day. So 250,000 barrels per day was estimated to have been displaced by bus fleets going electric. And the country that's doing the best job with bus fleets going electric is actually China. China's made incredible strides. We have interests in this rather unusual fuel here called a gas hydrate. So this substance here is something that's cold. It looks like ice. It would feel like ice. But it's an ice where you've got water molecules surrounding a methane molecule. And this is found off the east coast of New Zealand in the shallow seabed. Nowhere in the world knows how to produce this commercially yet, but some of the stuff we do in the department makes predictions of how much energy you could release from it. Catches, the predictions aren't particularly economically attractive, but there is a huge amount of gas in New Zealand and some other places like Japan, which have particular seabed conditions locked up out there and available. So if we chose to access it, if we accepted that gas needed to be much more expensive, there is resource out there that we could use if we made the choice. We're people who work with the entire energy sector. So we're people who are very kind of big system thinkers and think of all the possible actors in the energy sector. So I do a bit of work with the Business Energy Council here in some of their think tanks on what is the future of energy in terms of sort of implementation of commercial drivers, government policy drivers. How do all those features interact in terms of what our future could look like? So here they've got two different scenarios, Waka and Kayak, and different metrics on what they might look like as possible views of our future. Our future does include a carbon price. So we have people who are interested in carbon price. We have been consulting for the Interim Climate Change Commission to think about how the carbon price might move in the future. What impact does the $25 cap have? Does that cap have to move? Currently, is a $25 cap on carbon actually changing people's behaviour? There's other analysis around the world that says the price on carbon might have to go to $70 US per tonne. But what does that do for the rest of society if those impacts trickle through? And we also have a very strong interest in energy globally. So mainly through our geothermal program, but more recently through a wider program that I lead at master's level on energy. Energy is a very significant niche for New Zealand in terms of our renewable expertise. So New Zealand's electricity is 85% renewable, and we want to teach the world to do that. So this figure, most of you in the room are probably too young to remember Sir Rod Muldoon, former Prime Minister of New Zealand. He is opening there the first geothermal power station in Indonesia. So Indonesia is a very populous country kind of in our region, and we continue to support geothermal development in Indonesia, hosting many, many Indonesian students, often with government scholarships. I lead foreign aid projects in energy around the world. These days I've got a 2-year program on energy training in East Africa. So the University of Auckland is very proud of the commitment it has to working with the UN's Sustainable Development Goals around science and technology that brings clean, affordable energy to the world. And earlier this year, one of the university ratings agencies, Times Higher, created a rating system for university performance against the set of UN sustainability goals. And University of Auckland was ranked #1 in the world for delivering against those sustainability goals. So that was something that firstly surprised us. We're recording that. Yeah, I was surprised. I didn't see it coming. I didn't know much about this ranking exercise that was happening, but it is something that makes sense to me and that I'm very proud of. So that sort of wraps up some comments on what the Engineering Science Department does around energy. It gives you a sense of the applications. So we're very application driven, but at their core, everything we're doing there is driven by mathematically driven applications. So there's a lot of maths, physics, computer programming under those applications that allows us to be very analytical, either at a big sector, kind of national or global scale, or at a very technology-focused level. So slightly different talk to the stuff I talked about before. Really happy to take any questions anyone has in a group or individually about the Department of Engineering Science. And the ushers made me promise to tell you that if you arrived on a bus, the buses leave at 3:45. So thank you very much. I hope you've enjoyed your day. Thank you.